So here we go on question 2 on this little 3 problem set. We want to make ammonia, or what mass of ammonia can be produced from 15 liters of dry hydrogen. The dry hydrogen is nice because that means you don't have to deal with water vapor pressure. So we've got hydrogen plus nitrogen. That's going to make ammonia, NH3. Not balanced, so you put a 2 here and put a 3 here. All right, we have 15 liters of hydrogen, so that's 15 liters of that, but it's at 20 C and 1.2 atmospheres. Basic stoichiometry, what do you do in basic stoichiometry? You change to moles, then you do a mole ratio between ammonia and hydrogen, and then you change to grams, and that's it. So the only catch is you cannot use the 22.4 liters. So real quick, I'll show you how to do it both ways. So you got V1, V2, P1, P2, T1, T2. Since this 15 liters is at lab conditions, you could say it's 15 liters at 1.2 atmospheres and at 20 degrees C, so which is really 293 Kelvin. Okay, you could change it to standard, 273, and you could change the pressure to standard at 1. So then you take your 15 liters and change it to standard conditions. So if you did that, you'd have pressures going down, so volume goes up, so it'll be 1.2 over 1, sorry, as far as atmospheres are concerned. And the temperature's going down, so the volume would go down, so it'd be 273 over 293. All right, we would then be able to, let's find out what that volume is, so I'll stop and work it out right there. Okay, so 15 times 1.2 times 273, whoops, I hit the wrong number, 15 times 1.2 times 273, and then I'm going to divide that number by 293, and I get 16.77. So now we're going to change that many liters into moles. So put liters down here, put moles up here, and 1 mole is 22.4 liters. So why am I able to use that 22.4? Because I took this number and changed it to what it would be at standard conditions. I took the volume and adjusted it to standard conditions. Okay, so now if I take that number divided by 22.4, turns out that I have 0.75 moles of hydrogen. So I know I put moles of hydrogen on the bottom, moles of ammonia on top. 2 is 1. So that's 1.5 moles of ammonia, but go ahead and change it into grams. So we'd put moles of ammonia on the bottom, grams of ammonia on the top, and 17 grams are in 1 mole. So it's 1.5 times 17. So 0.75 times 2 ammonia times 2 and then times 17, 34 grams. Wait a minute, I think I did that wrong. Let me back that up. So I'm rushing. 0.75 times 2 times 17, 25.5 grams. So if you were wondering what I was doing, you were correct to wonder. Okay, so that's 25.5 grams of NH3. All right, there we go. Now the other way you could have done the problem is use the ideal gas law. So you could do PV equals nRT. You could put in 15 liters for volume. You could put in the pressure of 1.2 atmospheres, and for space I'm leaving out units. Put that decimal in there. We don't know the number of moles because that's what you're trying to find is the number of moles right here, trying to get to there. And R is 0.08205 because you're using the atmospheres this time for pressure. The temperature is 293 because 20 plus 273 is 293. Now to solve for n, we're going to do 1.2 times 15 and then divide by 0.08205, and then divide by 293, and I get 0.75 moles. So N equals 0.75 moles. Is that the same thing we got up here? Yes. So then we could take that 0.75 moles, put it in right here, do the same thing, and you get the same answer. So either way, it's 25.5. All right. Now we have the last question. You got decomposed sodium chlorate at room conditions. So you got sodium chlorate. Metallic chlorates decomposed to make metallic chlorides plus oxygen. You may remember that from your help sheet. And you got a balance of things. So you've got 3 O's, you got two O's, put a 3 here, put a 2 here, gives you 2 NA's, put a 2 here, there's the balance of the equation. Okay, you've got 375 grams of this. You're going to need to change this into moles, of course. So let's add up the formula weight of sodium chlorate. It is 23 plus 35.5 plus 48, and that equals 106.5. So 375 grams of sodium chlorate, grams on the bottom, moles on the top. One is 106.5 grams. And that is NaClO3. I better go ahead and write down everything. Grams of NaClO3. That would tell us that moles of NaClO3 need to go on the bottom. Moles of O2 go on the top. There are 3. There are 2. All right, 3 and 2 came from here and here, of course. Okay, so that gives us how many moles of oxygen? So 375 divided by 106.5. Then take that answer and multiply it by 3 halves, by 3, and then divide by 2. And I get 5.28. So 375 times 3, I'm just double checking my math, divided by 106.5, and then divide again by 2. 5.28. All right, so that's how many moles of oxygen we have. Now we got 2 options. You know the moles. If you do this, you could take 5.28 moles of O2 times moles of O2 on the bottom, liters, 22.4 liters is 1 mole. And that would give us 118 liters. But that would only be true at STP because the 22.4 is at STP. So then you would need to change your 118 liters. I'm going to write this instead. Well, I'll do it. I'll try and do it too. 118 liters to lab conditions. Okay, so V1 would be 118 liters. V2 we don't know. T1 this time would be standard because it's at standard. So that'd be 273. T2 would be lab temperature, which was 298. Okay, P1 would be standard, 101.3, and P2 would be the lab conditions, which would be 101.3 minus 3.2. Okay, now why would I take away the 3.2? Well, you remember, I'm going to go up here to show you this. So going up to the top here, I'm pretty sure I'm doing this by memory. I think 23.8 millimeters of mercury was the water vapor pressure at 25 degrees C. So I'm going to change that to kilopascals using standard pressure in kilopascals and standard pressure in millimeters of mercury. All right, so that would give us our answer in kilopascals, and that comes out to be 3.2. So 101.3 minus 3.2 is 98.1. So P2 is 98.1. Now that looks a little weird because you have 101.3 here and here. This is standard pressure. This was the pressure in the lab, but that included the water vapor. So we needed to subtract the water vapor to get the real pressure of the gas in the lab. So now to do the actual math, you come over here. I just try and squeeze it in over here. You got 118 liters. Temperature's going up. Volume goes up. 293 over 273. pressure goes down, volume goes up, 101.3 over 98.1. And our final answer then, I'll go ahead and work that math out. 100, oops. My phone forgot who I am. All right, here we go. So get my calculator going again. 118 multiplying by 293, multiplying by 101.3, dividing by 273, and dividing by 98.1. And I get 131 liters. All right, now the other way you could do the problem, we knew the moles of oxygen, so PV equals nRT. Pressure, we'd still have to use that adjusted pressure, be 98.1, so you do have to adjust the pressure in this technique. Volume we don't know. N we knew was 5.28. Since this is in kilopascals, we're going to use the 8.31, and the temperature is 298. So 5.28 times 8.31 times 298, and I'm going to divide that number by 98.1, and I get this time I got 133, which is close to this number, and that's probably a rounding error that I made somewhere, but I don't know where. And my wife called and told me I had to go home. So anyway, this is very close to this number. It should give you the same answer. So you can do it either way. Once you have moles, you can use the 22.4 and then change from lab to, once you have the moles, you can multiply by 22.4, and you know the volume here. So you can take the volume and change it from standard to lab conditions. Or you can take the 5.28 moles and use PV equals nRT. All right, so I hope that helped. I'm going to stop there, and if you can do these problems, you'll be fine on this test.